Universe together in a vast web of cosmic connectivity. Cosmic filaments. Ever wondered what holds the universe together in a vast web of cosmic connectivity? Cosmic filaments, the universe's grand highways, stretch across billions of light-years, linking galaxies, stars, and dark matter in a delicate, almost invisible lattice. How do these structures form, and what secrets do they reveal about the universe's evolution? Join us as we unravel 10 fascinating facts about cosmic filaments and their pivotal role in the cosmic web. Cosmic filaments are the universe's largest structures. Cosmic filaments are not just large, they are the largest known structures in the universe, stretching for hundreds of millions of light-years. These colossal threads of matter weave a framework connecting galaxies, clusters, and superclusters in a massive web-like pattern. The filaments form part of the cosmic web, a term that describes the large-scale structure of the universe. Made primarily of dark matter, gas, and galaxies, these filaments are bound together by gravity. Their immense size and intricate design reveal the universe's organization on its largest scale. Through simulations and observations, scientists have mapped out these filaments, showing how they thread through vast voids of seemingly empty space. The filaments' intersections are hubs where galaxy clusters form, while their threads serve as highways along which galaxies and matter travel. What's truly fascinating is how these structures emerged from tiny density fluctuations after the Big Bang. Over billions of years, gravity sculpted these filaments, transforming the chaotic early universe into the interconnected masterpiece we observe today. Dark matter is the backbone of cosmic filaments. While visible galaxies may outline cosmic filaments, it's dark matter that forms their backbone. This mysterious substance, which makes up about 27% of the universe's mass energy content, is largely responsible for the gravitational pull that shapes and holds these structures together. Dark matter doesn't interact with light or normal matter directly, making it invisible and detectable only through its gravitational effects. Scientists have used advanced simulations and techniques like gravitational lensing to understand how dark matter forms the scaffolding of the cosmic web. As dark matter clumps together, it creates gravitational wells that attract ordinary matter, forming the galaxies and stars that we see within filaments. This interaction between dark matter and visible matter highlights the unseen forces that govern the cosmos. By studying cosmic filaments, researchers hope to unlock more about the elusive nature of dark matter. These massive structures serve as laboratories for testing theories and understanding how dark matter influences the universe's evolution on grand scales. Filaments act as cosmic highways for galaxies. Cosmic filaments don't just connect galaxies, they guide their movement. Galaxies travel along these vast structures, influenced by the gravitational pull of dark matter and the underlying filamentary network. This movement isn't random. It follows a pattern that scientists refer to as cosmic flow. Galaxies and matter stream along the filaments toward denser regions like clusters and superclusters. This flow creates a dynamic, ever-evolving cosmic web, where filaments serve as pathways for the redistribution of matter. The role of filaments extends beyond mere transportation. They also influence galaxy formation and evolution. As galaxies travel through these dense regions, they interact with the hot gas and other matter within the filaments, which can trigger star formation or even strip galaxies of their gas, affecting their development. Observations from telescopes like the Sloan Digital Sky Survey and simulations like the Millennium Simulation have provided detailed maps of these flows, showcasing the intricate ballet of matter along the filaments. These studies highlight the filament's importance in shaping the universe's structure and dynamics. Cosmic filaments contain vast reservoirs of gas. Beyond galaxies and dark matter, cosmic filaments hold enormous amounts of diffuse gas, often referred to as the intergalactic medium. This gas, primarily hydrogen, fills the spaces between galaxies and serves as the raw material for star and galaxy formation. Recent observations have shown that these gas reservoirs can be incredibly hot, reaching temperatures of millions of degrees. This hot gas emits X-rays, which astronomers use to study the filament's composition and distribution. Advanced telescopes like the Chandra X-ray Observatory have been instrumental in revealing the properties of this hidden gas. The gas within filaments also provides clues about the universe's chemical evolution. Elements like carbon, oxygen, and iron, produced by stars and supernovae, are dispersed into the filaments, enriching the intergalactic medium over time. These gaseous reservoirs play a vital role in the cosmic ecosystem, fueling galaxy growth and maintaining the balance of matter across the universe. By studying the gas and filaments, scientists gain insights into the processes that drive the universe's ongoing evolution. Filaments influence the growth of galaxy clusters. At the intersections of cosmic filaments lie galaxy clusters, some of the most massive structures in the universe. These clusters form where multiple filaments converge, creating regions of intense gravitational pull that attract vast amounts of matter. The role of filaments in cluster formation is profound. As matter flows along the filaments, it accumulates at these intersections, fueling the growth of clusters. This process, known as hierarchical clustering, is a cornerstone of modern cosmology, explaining how structures grow over time. Galaxy clusters within filaments are often connected by bridges of matter, visible as faint X-ray emissions or gravitational lensing patterns. These connections provide direct evidence of the cosmic web's interconnected nature and its role in shaping the universe. Understanding how filaments feed galaxy clusters helps scientists unravel the complex processes behind structure formation. Observations of clusters and their surrounding filaments also shed light on the behavior of dark matter and the distribution of energy in the cosmos. Filaments shape the universe's cosmic landscape. Cosmic filaments are more than just physical structures, they define the universe's large-scale geometry. Their intricate patterns of dense threads and empty voids create a tapestry that reflects the underlying physics of the cosmos. This cosmic landscape is a direct result of initial conditions set by the Big Bang. Tiny fluctuations in the density of matter expanded and grew under the influence of gravity, creating the web-like structure we see today. The study of these patterns provides critical information about the universe's origins and its subsequent evolution. The cosmic web also serves as a testing ground for theories about dark energy, the mysterious force driving the universe's accelerated expansion. By analyzing how filaments and voids evolve over time, scientists can probe the effects of dark energy on the universe's structure. Filaments are not static, they change and evolve, influenced by gravitational interactions, galaxy movements, and cosmic expansion. This dynamic nature adds to the richness of the cosmic web and underscores its role as a living, evolving system. Filaments are a bridge between galaxies and voids. Cosmic filaments don't just connect galaxies, they serve as a transition zone between the dense hubs of galaxy clusters and the vast empty expanses known as cosmic voids. These voids, which make up most of the universe's volume, are regions with few or no galaxies, and filaments act as the intricate threads bordering these immense regions of emptiness. The boundaries between filaments and voids are fascinating areas of study as they represent a stark contrast in the density of matter. Filaments are rich with galaxies, gas, and dark matter, while voids are relatively barren, containing only traces of matter. This contrast creates unique environments where scientists can study the forces shaping the universe. Galaxies near the edges of filaments experience gravitational influences that can affect their shape, speed, and evolution. As galaxies fall into filaments from voids, they often encounter streams of gas and dark matter that fuel star formation or alter their structure. These interactions highlight the dynamic relationship between dense filaments and the vast voids they surround. Exploring this bridge between galaxies and voids offers valuable insights into how matter is distributed and how different environments influence the evolution of cosmic structures. Filaments not only connect the universe but also define its boundaries, shaping the interplay between its densest and emptiest regions. The cosmic web illuminates the universe's early days. The study of cosmic filaments has become a powerful tool for understanding the universe's origins. These structures hold clues about the conditions of the early universe, particularly the moments following the Big Bang when the first density fluctuations began to take shape. Using advanced simulations and telescopes, scientists can trace the evolution of filaments back billions of years. The earliest filaments formed when tiny density variations in the primordial universe grew under the influence of gravity. These early threads laid the foundation for the massive cosmic web we see today. The distribution and alignment of filaments also provide information about the physics of the early universe. For example, studying how filaments are oriented and how galaxies are distributed within them, can reveal the effects of cosmic inflation, the rapid expansion that occurred just after the Big Bang. By observing ancient light, such as the cosmic microwave background, and mapping the positions of galaxies and filaments, researchers piece together a timeline of cosmic evolution. The story of filaments is not just about the present-day universe, but also about the profound forces that shaped it from the very beginning. Filaments may harbor missing baryonic matter. For years, scientists have been searching for the universe's missing baryonic matter, the ordinary matter composed of protons, neutrons, and electrons that make up stars, planets, and people. Observations suggest that much of this baryonic matter is unaccounted for, and cosmic filaments may hold the answer. Research indicates that this missing matter resides in the hot, diffuse gas within filaments, known as the warm-hot intergalactic medium. This gas, spread out across the vast stretches of the cosmic web, is difficult to detect directly but emits faint X-rays and ultraviolet light that specialized telescopes can observe. Studies using telescopes like the Chandra X-ray Observatory and the Hubble Space Telescope have confirmed the presence of this gas, providing a clearer picture of where the universe's baryonic matter is hiding. This discovery helps resolve one of cosmology's biggest mysteries and underscores the significance of filaments as reservoirs of cosmic material. Understanding the distribution of baryonic matter in filaments also sheds light on galaxy formation, star birth, and the dynamics of the intergalactic medium. Filaments are not just highways for galaxies, but also storehouses of the universe's fundamental building blocks. Cosmic filaments are a glimpse into the universe's future. The cosmic web, with its sprawling filaments and dense clusters, is constantly evolving. Over billions of years, gravitational forces continue to pull matter along filaments toward the densest regions, causing clusters and superclusters to grow even larger. This gradual process offers a glimpse into the universe's future. As filaments funnel matter into these hubs, the surrounding regions become emptier, creating more pronounced voids. The cosmic web structure becomes increasingly defined, with sharper contrast between dense filaments and vast voids. This ongoing evolution highlights the universe's dynamic nature and the powerful role of gravity in shaping its fate. Dark energy, the mysterious force driving the accelerated expansion of the universe, also plays a role in the future of filaments. As space expands, the distances between filaments and clusters will grow, potentially halting the flow of matter. This expansion may eventually isolate galaxy clusters, making the universe appear more fragmented over time. The study of filaments is not just about understanding the past and present, but also about predicting the cosmic landscape billions of years from now. These vast structures remind us that the universe is a work in progress, constantly shifting and evolving toward its ultimate destiny. And there you have it. 10 incredible facts about cosmic filaments, the universe's grand connectors that weave together galaxies, clusters, and dark matter in an intricate web. From their formation after the Big Bang to their role in shaping the universe's future, these filaments reveal the profound beauty and complexity of the cosmos. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of the universe with us. Have you ever wondered what the future holds for our Milky Way? From merging with distant galaxies to evolving into something entirely unrecognizable, the possibilities are as vast as the universe itself. What will happen to the stars, planets, and even the supermassive black hole at its center? Join us as we unravel 7 fascinating theories about the Milky Way's future and discover the secrets hidden in the cosmos that could shape it for billions of years to come. Galactic Collision with Andromeda, written by Graham Wilson. The Milky Way and the Andromeda Galaxy are on an inevitable path toward each other, set to collide in about 4.5 billion years. This isn't a catastrophic crash as you might expect, but rather a slow-motion cosmic ballet that will reshape both galaxies over millions of years. Despite the immense scale of these galaxies, the vast distances between stars make actual stellar collisions highly unlikely. Instead, gravity will take center stage, pulling and warping these colossal structures in a dramatic merger. As the galaxies draw closer, they'll start to tug on each other with their immense gravitational forces. Stars from both galaxies will begin shifting into elongated streams, creating dazzling arcs of light across the cosmos. The Milky Way's familiar spiral structure will be stretched and distorted, and Andromeda's stars will swirl into an entirely new configuration. During this time, gas clouds from the two galaxies may collide, sparking bursts of star formation. These regions of new stars will shine brilliantly, lighting up the heavens in ways we can only dream of witnessing. At the heart of this collision lies a captivating event. Both the Milky Way and Andromeda harbor supermassive black holes at their centers, and as the galaxies merge, these black holes will spiral toward each other. When they finally combine, they'll form an even larger black hole, releasing immense energy in the form of gravitational waves. This event will forever alter the core of the new galaxy, likely creating a stunning luminous center surrounded by billions of stars. The result of this epic merger will be a new galaxy often referred to as Milkomeda. Its shape will be more elliptical than the spiral we know today, marking a profound transformation in the structure of our cosmic home. While this collision may sound alarming, it's a natural part of galactic evolution. It's a reminder of how dynamic and interconnected our universe truly is, with galaxies constantly evolving through interactions that shape their destinies. Dark energy and galactic expansion. The universe is expanding, and it's doing so faster than ever before, thanks to a mysterious force called dark energy. This elusive phenomenon makes up about 68% of the total energy in the universe, yet it's one of the least understood aspects of modern science. Discovered in the late 1990s, dark energy was revealed through observations of distant supernova that showed galaxies are not just moving away from each other, they're accelerating outward. This finding was groundbreaking and challenged everything we thought we knew about the cosmos. Dark energy acts like an invisible pressure, counteracting the pull of gravity on the largest scales. Instead of galaxies being drawn back together, dark energy pushes them apart, stretching the very fabric of spacetime. To grasp this, think about a balloon being inflated. Every point on its surface moves away from every other point as the balloon expands. In our universe, galaxies are those points, and space itself is the balloon. What's even more intriguing is that this expansion doesn't slow down. It speeds up over time, making the universe larger and emptier as billions of years pass. Theories about the nature of dark energy are still evolving. Some scientists suggest it could be linked to the energy of the vacuum in space, an idea tied to quantum mechanics. Others propose it might be an entirely new force of nature, or even a misunderstanding of how gravity works on cosmic scales. What's certain is that dark energy holds the key to understanding the ultimate fate of the universe. Will the expansion continue indefinitely, leading to a cold, dark cosmos? Or could it slow down and reverse, collapsing everything into a big crunch? These are questions that physicists and astronomers are racing to answer. Dark energy doesn't just expand our universe, it expands our sense of wonder. It reminds us of how much we still have to learn about the cosmos and the forces that govern it. As telescopes like the James Webb Space Telescope and upcoming missions like the Nancy Grace Roman Space Telescope dive deeper into the mysteries of dark energy, we may uncover answers that completely reshape our understanding of the universe's past, present, and future. Stellar evolution and galactic recycling. Stars are more than just points of light in the night sky. They are the engines that power the universe and the source of nearly every element we know. Stellar evolution describes the life cycle of stars, from their fiery beginnings to their spectacular endings. When stars form, they are born from vast clouds of gas and dust called nebulae. Over millions of years, gravity pulls this material together, igniting nuclear fusion at their cores. This process is what makes stars shine and what drives the creation of new elements, transforming hydrogen and helium into the heavier elements essential for life. As stars age, their fate depends on their size. Smaller stars, like our Sun, expand into red giants before shedding their outer layers to form beautiful planetary nebulae, leaving behind dense white dwarfs. Massive stars, on the other hand, end their lives with a bang, literally. They explode in supernovae, scattering their elements across space. These dramatic events forge the heaviest elements like gold and uranium, which are then dispersed into the galaxy. Supernovae don't just create new elements, they also enrich the surrounding interstellar medium, seeding the galaxy with the raw materials needed for the next generation of stars. This process is what we call galactic recycling. The material from dying stars doesn't go to waste. It's recycled into new stars, planets, and even life. When these enriched clouds of gas and dust collapse to form new stars, the cycle begins anew. Over billions of years, this continuous process has transformed the universe, shaping galaxies and providing the building blocks for everything we see today. It's incredible to think that the carbon in your body or the iron in your blood was forged in the heart of a star billions of years ago. Stellar evolution and galactic recycling are a testament to the interconnected nature of the cosmos. They show us that nothing in the universe truly ends, it simply changes form, contributing to something greater. As we study the life and death of stars, we not only learn about the mechanics of the universe but also gain a deeper appreciation for our place within it. Each star's life is part of an ongoing story, a story that connects us all to the very fabric of the cosmos. Supermassive black hole activity. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass equivalent to about 4 million suns. Though currently in a relatively quiet state, black holes like this can undergo periods of intense activity, particularly when large amounts of gas, dust, or even stars are drawn into their gravitational pull. When this happens, the material forms an accretion disk around the black hole, heating up and emitting enormous amounts of energy. The future of our galaxy could see Sagittarius A* awakening, transforming the Milky Way center into an active galactic nucleus. This could create spectacular jets of energy and radiation, similar to what we observe in quasars in distant galaxies. Such activity wouldn't just light up the galactic core, it could also disrupt the surrounding region, triggering star formation in some areas while clearing out gas and dust in others. The black hole's behavior is influenced by the galaxy's evolution. As the Milky Way interacts with its neighbors, material from these interactions could fuel Sagittarius A*, igniting its activity. On the other hand, the depletion of available material over time could leave it dormant for billions of years. Either way, the black hole remains a central player in the galaxy's future. Studying Sagittarius A* helps us understand not just our galaxy, but the role supermassive black holes play in shaping galaxies throughout the universe. Whether it remains a quiet observer or becomes an active force, its presence ensures that the center of the Milky Way will continue to be a source of cosmic intrigue. The role of dark matter in galactic evolution. Dark matter is one of the most mysterious forces in the universe, and it plays a crucial role in the evolution of galaxies like the Milky Way. Although we can't see or directly detect dark matter, we know it's there because of its gravitational effects on stars, gas, and other visible matter. Dark matter acts as the glue that holds galaxies together, forming a vast halo around the Milky Way that influences its shape and behavior. Over time, the distribution of dark matter within the Milky Way will change, driven by gravitational interactions and the movement of matter within the galaxy. This could lead to shifts in the galaxy's structure, influencing the shape of its spiral arms and the density of its core. Dark matter may also play a role in the Milky Way's eventual collision with Andromeda, determining how the two galaxies merge and what the resulting structure will look like. Dark matter doesn't just affect the galaxy's structure, it also impacts its ability to form stars. By creating regions of higher gravitational pull, dark matter helps gather gas and dust into dense clouds where new stars are born. As the galaxy evolves and its gas reserves dwindle, the interplay between dark matter and visible matter will determine whether star formation can continue, or if the galaxy will enter a quieter phase. Understanding dark matter is one of the greatest challenges in modern astrophysics. As we study its role in the Milky Way, we're not only uncovering the secrets of our galaxy's future, but also piecing together the larger puzzle of the universe itself. Dark matter might be invisible, but its impact is written across the cosmos in every star, planet, and galaxy we see. The birth of new galactic structures. Galaxies are constantly evolving, and the Milky Way is no exception. Over time, gravitational interactions and the movement of stars reshape their structure, giving rise to new features like star clusters and spiral arm patterns. These changes are fueled by the interplay of visible matter like stars and gas, and the dark matter that forms the galaxy's unseen framework. This dynamic process ensures that our galaxy remains vibrant and active, not a static relic of the past. The spiral arms of the Milky Way are particularly fascinating. These regions are not fixed structures but rather areas of higher density where stars and gas pass through, triggering new waves of star formation. The result is a constantly changing cosmic tapestry that adds to the galaxy's beauty and complexity. These arms act as stellar nurseries, producing brilliant clusters of young stars that illuminate the galaxy's outer edges. At the galaxy's center, the bar-shaped structure plays a crucial role. It channels gas and stars toward the core, fueling the activity around the supermassive black hole, Sagittarius A*. This process can lead to bursts of star formation and even influence the galaxy's overall shape. As the bar evolves, it may drive changes that shift the Milky Way from its current spiral configuration to something entirely new, like a lenticular galaxy. The Milky Way's ability to create and adapt its structures reflects the ongoing processes that define galaxies. As it interacts with neighboring galaxies and absorbs new material, its appearance will continue to change. This constant evolution ensures that the story of the Milky Way is one of transformation, a reminder of the dynamic nature of the universe. Galactic interactions beyond Andromeda. The Milky Way is not an isolated entity, it's part of a larger family of galaxies known as the Local Group. While the collision with Andromeda often dominates discussions about the galaxy's future, interactions with smaller neighbors like the Magellanic Clouds also play a significant role. These dwarf galaxies are gradually merging with the Milky Way, contributing gas, stars, and dark matter to its structure. The large and small Magellanic Clouds in particular are creating dramatic effects. Streams of gas known as the Magellanic Stream connect these galaxies to the Milky Way, fueling star formation in our galaxy's outskirts. These interactions highlight how even small galaxies can leave lasting imprints on their larger counterparts. Beyond the Local Group, the Milky Way exists within the Virgo supercluster, a massive network of galaxies held together by gravity. Over billions of years, the Milky Way will interact with this larger cosmic structure, experiencing gravitational influences that could reshape its trajectory and structure. These distant interactions remind us that galaxies are not static islands but part of an interconnected cosmic web. The constant dance of galactic interactions ensures that the Milky Way's future will be shaped by both nearby and distant forces. From the pull of neighboring galaxies to the overarching influence of the cosmic web, these connections remind us of the dynamic and ever-changing nature of the universe. Each interaction is a chapter in the Milky Way's ongoing story of evolution and transformation. That concludes our journey through 7 captivating theories about the Milky Way's future. From cosmic collisions to the mysterious effects of dark energy, our galaxy's destiny is as fascinating as the stars within it. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of the universe with us. The night sky has been a source of wonder for thousands of years. Ancient civilizations looked up and saw more than just stars. They saw legends, gods, and epic battles written across the cosmos. But what if some of the most famous constellations had stories even more incredible than you imagined? From heroic battles to tragic love tales, these celestial patterns hold secrets that have stood the test of time. Join us on this journey through the myths and mysteries of 7 famous constellations where history and mythology collide in the stars above. Orion, the Mighty Hunter. The constellation of Orion is one of the most recognizable in the night sky, but its story is anything but simple. In Greek mythology, Orion was a giant hunter, said to be the son of Poseidon. His incredible strength and skill made him a favorite of the gods, yet his arrogance led to his downfall. Some versions of the myth say that he boasted he could hunt and kill every animal on Earth, enraging Gaia, the goddess of the Earth. To punish him, she sent a giant scorpion to strike him down. Others say he was slain by the goddess Artemis, either in a tragic accident or because of his pursuit of her. No matter the version, Orion's death was honored by Zeus, who placed him among the stars, forever locked in battle with the Scorpius constellation. The celestial figure of Orion is easy to spot thanks to its distinctive belt of 3 bright stars, Alnitak, Alnilam, and Mintaka. His raised arm and outstretched bow create the image of a warrior mid-hunt, while his faithful hunting dogs, represented by the Canis Major and Canis Minor constellations, remain by his side. The bright star Betelgeuse marks his shoulder, glowing red like the blood of the wounded hunter, while Rigel, a dazzling blue giant, defines one of his feet. Orion's position in the sky shifts with the seasons, appearing in full prominence during winter in the northern hemisphere. Beyond mythology, Orion is home to one of the most famous celestial wonders, the Orion Nebula. This massive cloud of dust and gas is a stellar nursery where new stars are born. Astronomers have studied it for centuries, uncovering secrets about the formation of galaxies. The nebula's glow, visible even with small telescopes, serves as a reminder that the stories of the stars are always evolving. Even though Orion's legend is ancient, the science behind its stars continues to unfold, proving that mythology and astronomy are forever intertwined. Ancient cultures across the world had their own interpretations of Orion. The Egyptians associated it with Osiris, the god of the afterlife, believing that the stars of Orion aligned with the pyramids of Giza to guide the pharaohs to eternity. The Chinese saw it as a powerful warrior figure in their mythology, while Native American tribes had stories of Orion as a celestial guardian. Across civilizations, Orion has remained a symbol of strength, adventure, and destiny, one of the few constellations to bridge cultures and connect humanity through the ages. Ursa Major, the Great Bear. The constellation of Ursa Major, best known for containing the Big Dipper, carries a story of betrayal, revenge, and divine intervention. In Greek mythology, it represents Callisto, a nymph who was a companion of Artemis. Callisto's beauty caught the attention of Zeus, who fell in love with her. When she bore his child, Hera, the jealous wife of Zeus, was furious. As punishment, Hera transformed Callisto into a bear, leaving her to wander the forests alone. Years later, her son Arcas nearly killed her in a hunting accident, not recognizing that the bear was his mother. To prevent the tragedy, Zeus intervened, placing them both in the sky, Callisto as Ursa Major and Arcas as the smaller constellation, Ursa Minor. Ursa Major is one of the largest and most recognizable constellations in the night sky. The 7 brightest stars form the Big Dipper, which serves as a celestial compass. The 2 outer stars of the Dipper's bowl, Dubhe and Merak, point directly to Polaris, the North Star, making it an essential navigation tool for explorers throughout history. The constellation's shape shifts slightly with the seasons, but it remains a reliable presence, guiding travelers across oceans and deserts for millennia. Astronomers now know that the stars forming Ursa Major are not just a random grouping. Many of them belong to a moving star cluster called the Ursa Major Moving Group, traveling together through space. The constellation also contains fascinating deep sky objects like the Pinwheel Galaxy and Bode's Galaxy, both visible with modest telescopes. These distant worlds remind us that even familiar constellations hide incredible astronomical discoveries. Many cultures have their own interpretation of Ursa Major. In Native American legends, the bear is often depicted as being chased by hunters, represented by the stars of the Dipper's handle. The Iroquois believed the bear was pursued through the sky with its blood falling each autumn, turning the leaves red. In Hindu mythology, the 7 stars of the Dipper are linked to 7 great sages, the Saptarishi, who hold cosmic wisdom. Across cultures, Ursa Major has been a symbol of power, endurance, and the mysteries of the cosmos. Cassiopeia, the Vein Queen. Cassiopeia, the striking W-shaped constellation, tells a tale of arrogance and punishment. In Greek mythology, Cassiopeia was the queen of Ethiopia and the mother of Andromeda. She was known for her beauty, but also for her pride. According to legend, Cassiopeia claimed that she and her daughter were more beautiful than the sea nymphs, the Nereids. This angered the sea god Poseidon, who sent a monstrous sea creature to ravage their kingdom. To appease the wrathful deity, Andromeda was chained to a rock as a sacrifice. However, before the beast could claim her, the hero Perseus arrived, using the severed head of Medusa to turn the monster to stone, saving Andromeda. Despite her daughter's rescue, Cassiopeia did not escape divine punishment. Zeus placed her in the sky, but in a position of eternal humiliation. The constellation Cassiopeia circles the North Star and appears upside down for half the night as if she is hanging from her throne in disgrace. The 5 bright stars that form the W shape represent her seated position. yet her regal posture cannot save her from the cosmic lesson on vanity and arrogance. Astronomically, Cassiopeia is rich in celestial wonders. The constellation is home to the famous Heart and Soul nebulae, vast regions of cosmic dust where new stars are born. It also contains the star cluster NGC 457, often called the Owl Cluster or the ET Cluster due to its striking resemblance to a pair of eyes staring from deep space. These celestial features make Cassiopeia a favorite among astronomers and stargazers alike. Various cultures have reimagined Cassiopeia in different ways. In some Norse traditions, she was seen as a hand or a chariot, while in Arabic astronomy, the W shape was interpreted as a camel. Yet across civilizations, the story of Cassiopeia remains a warning against unchecked pride, a reminder that even in the heavens arrogance has consequences. Perseus, the hero in the stars. The constellation of Perseus shines as a tribute to one of Greek mythology's greatest heroes. Perseus, the son of Zeus and Danae, is best known for slaying the Gorgon Medusa. With the aid of the gods, he received a mirrored shield from Athena, a helmet of invisibility from Hades, winged sandals from Hermes, and a magical sword from Hephaestus. Armed with these divine gifts, he avoided Medusa's deadly gaze, beheaded her, and later used her severed head to defeat various enemies, including the sea monster that threatened Andromeda. In the night sky, Perseus is depicted holding Medusa's head, represented by the bright star Algol. Known as the Demon Star, Algol is one of the first variable stars ever discovered, dimming and brightening over time. Ancient astronomers noticed its eerie flickering and associated it with the evil eye of Medusa, a fitting celestial feature for the legendary monster slayer. Perseus is also home to the stunning double cluster, a pair of open star clusters that sparkle like distant jewels. Another highlight of the constellation is the Perseid meteor shower, an annual event that lights up the sky every August as Earth passes through the debris of the comet Swift-Tuttle. The meteors streak across the heavens as if Perseus himself is still battling celestial foes. Different cultures have their own take on Perseus. Some see him as a warrior protecting the heavens, while in Hindu mythology, parts of the constellation are linked to the hero Parashurama. No matter the interpretation, Perseus remains a symbol of bravery, reminding us that even among the stars, heroism never fades. Draco, the celestial dragon. Coiled among the stars, the constellation Draco tells a tale of a fearsome guardian defeated by the gods. In Greek mythology, Draco is associated with Ladon, the dragon that guarded the golden apples in the Garden of the Hesperides. These apples granted immortality, and Ladon's task was to ensure no one stole them. However, during his 12 labors, Hercules was ordered to retrieve the apples. Using his legendary strength, he slew the dragon, allowing him to complete his task. As a reward for its eternal vigilance, Zeus placed Ladon among the stars. Draco winds its way across the sky, forming one of the longest constellations in the northern hemisphere. It encircles the North Pole, never setting below the horizon in many parts of the world. Its shape resembles a twisting serpent, with its head marked by the bright star El Tanin, which means dragon's head in Arabic. In astronomy, Draco holds some of the most fascinating celestial bodies. The Cat's Eye Nebula, a breathtaking planetary nebula, lies within its boundaries, resembling a glowing cosmic eye peering into space. The constellation is also home to Thuban, a star that once served as Earth's North Star over 4,000 years ago, during the time of the ancient Egyptians. Dragons appear in myths across cultures. In Chinese mythology, celestial dragons were seen as symbols of wisdom and power, controlling rivers and the elements. In Norse legends, a dragon called Nidhogg gnawed at the roots of the world tree. No matter the culture, Draco remains a symbol of strength, mystery, and the eternal battle between heroes and monsters. Pegasus, the winged stallion. Pegasus, the magnificent winged horse, has long been a symbol of speed, wisdom, and divine power. In Greek mythology, he was born from the blood of Medusa after Perseus beheaded her. Pegasus played a crucial role in many legends, including carrying the hero Bellerophon to battle the fearsome Chimera, a fire-breathing monster with the body of a lion, the head of a goat, and a serpent's tail. However, Bellerophon grew too arrogant, attempting to fly to Mount Olympus. As punishment, Zeus caused Pegasus to throw him off, sending him crashing back to Earth. Pegasus, on the other hand, was rewarded with a place among the stars. Pegasus is one of the largest constellations in the night sky. Its defining feature is the Great Square of Pegasus, a giant celestial landmark made of 4 bright stars. This square serves as a gateway to finding other deep sky objects, including the Andromeda Galaxy, our nearest galactic neighbor, located just outside the constellation's boundary. The constellation also contains the Einstein Cross, a phenomenon caused by gravitational lensing, where the light of a distant quasar is bent around a closer galaxy, creating multiple images of the same object. This incredible cosmic effect proves that even in mythology-inspired constellations, modern science continues to reveal new wonders. Throughout different cultures, Pegasus has symbolized freedom, inspiration, and divine intervention. The Romans associated him with poetry and wisdom, believing that the stamp of his hoof created the sacred spring of Hippocrene, a source of artistic inspiration. Pegasus remains a reminder that dreams can soar, but hubris can lead to a great fall. Andromeda, the chained princess in the sky. Andromeda, a constellation named after a tragic yet resilient princess, carries one of the most famous myths in Greek mythology. According to legend, Andromeda was the daughter of King Cepheus and Queen Cassiopeia of Ethiopia. Her mother, in her vanity, claimed that she was more beautiful than the sea nymphs, the Nereids. Enraged by this arrogance, Poseidon, the god of the sea, sent a monstrous sea creature to ravage their kingdom. To appease the wrathful deity, the desperate king and queen chained Andromeda to a rock by the shore as a sacrifice to the beast. Just as the monster was about to strike, the hero Perseus arrived, fresh from slaying the Gorgon Medusa. Using Medusa's severed head, he turned the sea monster to stone and saved Andromeda. The two were later wed, and as a reward for her suffering and endurance, the gods placed Andromeda's image among the stars. The Andromeda constellation is best known for being home to the Andromeda Galaxy, the closest spiral galaxy to our own Milky Way. Visible to the naked eye from dark sky locations, this massive galaxy stretches over 220,000 light-years in diameter and contains an estimated trillion stars. It is also on a collision course with our galaxy, predicted to merge with the Milky Way in about 4.5 billion years. This cosmic event will reshape the night sky forever, giving future generations an entirely new celestial landscape. The Andromeda constellation itself is easy to locate in the northern hemisphere, sitting next to Pegasus, the winged horse, and forming a bridge between several well-known star patterns. The stars of Andromeda have played a role in various cultures beyond Greek mythology. In ancient Arabic astronomy, some of its brightest stars were considered part of a larger constellation representing a fish, while in Chinese mythology, they were part of a celestial palace. In modern times, astronomers have used the Andromeda Galaxy as a critical reference point for studying the expansion of the universe. The galaxy's movement and its eventual collision with the Milky Way provide key insights into the fate of cosmic structures over billions of years. Beyond the myths and scientific discoveries, Andromeda remains one of the most awe-inspiring constellations. Whether you admire it for its tragic yet heroic story, its place in celestial history, or the breathtaking view of its galaxy, Andromeda is a reminder that the universe is not just a collection of distant lights. It is a canvas where stories, science, and the future of space exploration all intertwine. When you look up at the night sky, you're not just seeing stars, you're witnessing the echoes of ancient legends and the unfolding mysteries of the cosmos. As we wrap up our journey through these fascinating constellations, remember that every star in the night sky carries a story. Tales of heroes, monsters, and celestial wonders that have inspired cultures for thousands of years. Whether you're gazing up at Orion, Cassiopeia, or Draco, you're looking at myths written in the cosmos. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep discovering the world's wonders with us. Ever wondered what holds the universe together in a vast web of cosmic connectivity? Cosmic filaments, the universe's grand highways, stretch across billions of light-years, linking galaxies, stars, and dark matter in a delicate, almost invisible lattice. How do these structures form, and what secrets do they reveal about the universe's evolution? Join us as we unravel 10 fascinating facts about cosmic filaments and their pivotal role in the cosmic web. Cosmic filaments are the universe's largest structures. Cosmic filaments are not just large, they are the largest known structures in the universe, stretching for hundreds of millions of light-years. These colossal threads of matter weave a framework connecting galaxies, clusters, and superclusters in a massive web-like pattern. The filaments form part of the cosmic web, a term that describes the large-scale structure of the universe. Made primarily of dark matter, gas, and galaxies, these filaments are bound together by gravity. Their immense size and intricate design reveal the universe's organization on its largest scale. Through simulations and observations, scientists have mapped out these filaments, showing how they thread through vast voids of seemingly empty space. The filaments' intersections are hubs where galaxy clusters form, while their threads serve as highways along which galaxies and matter travel. What's truly fascinating is how these structures emerged from tiny density fluctuations after the Big Bang. Over billions of years, gravity sculpted these filaments, transforming the chaotic early universe into the interconnected masterpiece we observe today. Dark matter is the backbone of cosmic filaments. While visible galaxies may outline cosmic filaments, it's dark matter that forms their backbone. This mysterious substance, which makes up about 27% of the universe's mass energy content, is largely responsible for the gravitational pull that shapes and holds these structures together. Dark matter doesn't interact with light or normal matter directly, making it invisible and detectable only through its gravitational effects. Scientists have used advanced simulations and techniques like gravitational lensing to understand how dark matter forms the scaffolding of the cosmic web. As dark matter clumps together, it creates gravitational wells that attract ordinary matter, forming the galaxies and stars that we see within filaments. This interaction between dark matter and visible matter highlights the unseen forces that govern the cosmos. By studying cosmic filaments, researchers hope to unlock more about the elusive nature of dark matter. These massive structures serve as laboratories for testing theories and understanding how dark matter influences the universe's evolution on grand scales. Filaments act as cosmic highways for galaxies. Cosmic filaments don't just connect galaxies, they guide their movement. Galaxies travel along these vast structures, influenced by the gravitational pull of dark matter and the underlying filamentary network. This movement isn't random. It follows a pattern that scientists refer to as cosmic flow. Galaxies and matter stream along the filaments toward denser regions like clusters and superclusters. This flow creates a dynamic, ever-evolving cosmic web, where filaments serve as pathways for the redistribution of matter. The role of filaments extends beyond mere transportation. They also influence galaxy formation and evolution. As galaxies travel through these dense regions, they interact with the hot gas and other matter within the filaments, which can trigger star formation or even strip galaxies of their gas, affecting their development. Observations from telescopes like the Sloan Digital Sky Survey and simulations like the Millennium Simulation have provided detailed maps of these flows, showcasing the intricate ballet of matter along the filaments. These studies highlight the filament's importance in shaping the universe's structure and dynamics. Cosmic filaments contain vast reservoirs of gas. Beyond galaxies and dark matter, cosmic filaments hold enormous amounts of diffuse gas, often referred to as the intergalactic medium. This gas, primarily hydrogen, fills the spaces between galaxies and serves as the raw material for star and galaxy formation. Recent observations have shown that these gas reservoirs can be incredibly hot, reaching temperatures of millions of degrees. This hot gas emits X-rays, which astronomers use to study the filament's composition and distribution. Advanced telescopes like the Chandra X-ray Observatory have been instrumental in revealing the properties of this hidden gas. The gas within filaments also provides clues about the universe's chemical evolution. Elements like carbon, oxygen, and iron, produced by stars and supernovae, are dispersed into the filaments, enriching the intergalactic medium over time. These gaseous reservoirs play a vital role in the cosmic ecosystem, fueling galaxy growth and maintaining the balance of matter across the universe. By studying